Okay, hello, welcome again. So, in our previous module, as you can see, we have just simulated this NAND gate circuit, and we have explained thoroughly how we picked up this component from the library, how we define its spice model, how we refer to the data sheet of this NAND gate IC with this given number, how we choose the VCC supply voltage, and how we applied the inputs A and B that are varying with respect to time. So A input to the NAND gate is a frequency of 1 megahertz, and B input is a frequency of 0.5 megahertz because the period is 2 micron. So with that, we simulated our circuit by clicking the simulator button, and then we clicked here, and here we chose the transient analysis, and we said, okay, time step is about, let's say, 1 micron, or let's say 0.1 micron, and the final time is about 10 micron because our maximum clock here is 1 megahertz, or time period is 1 micron. So we chose a final time about 10 micron, and then we clicked OK. And then you see there are all signals highlighted here: input A, input B, and the output Y. Output Y is here. But before that, we click the run simulator button. The simulation is now being run and the results are ready. But when we plot here input A and input B, we analyze like, okay, red is the input A, blue is the input B, and that those two inputs are switching between logic high and logic low. And then on Y, that is the output in the schematic, is also given here. But you see now all these three signals, that is two inputs and one output, they are all on the same plot at the same row. So they are mixing with each other. So it is difficult for us to interpret and understand these results of NAND gate. We basically want to verify the truth table of a NAND gate. So to do that, what we can do is we just unselect this, and choose the option of adding external user defined signals. So we click simulation, then we click user defined signals, and here we see that we will click add field. Here we will type V, that is in bracket A, that is first signal, bracket close, and then we'll say plus 1. So it's like vertical distance we are saying, or maybe just keep it just V of A. But V of A is already here, so that will be confused. So why not just type plus A1 here, and then we'll click add field again. So first field has been added. Then we'll say V in bracket B, bracket close, and plus. Let's say plus, let's say 10. So there is a distance of 10 from the first signal in plotting the second signal. And then finally, we will want output to be plotted. So V of Y plus, we'll say like say 20, and we'll see how it goes. Okay. So you now see this is there. We can just close it, delete this final field. So we have got three signals, and we'll click OK. These signals are appearing here: VA of 1, VB of 10, and VY plus 10. It is the number we have added in addition is just to separate the signals from each other. So we'll click here first. So this is our input A, which is switching between logic 0 and logic high, which is in analog terms switching between the let's say 0 volts and the 5.5 volts. Then we have B. So B, not this B, but VB of 10. Now look at this. Now this is V of A and this is V of B. because this is 1 micron period signal, that is input A. This is 2 micron period signal. Okay. If you want to add the labels, click here and click go to plot setup and show legend, and then select OK. You see here the user 1 and user 0. But rather of doing that, I would suggest just go back, unselect, click OK, and rely on these colors. So the orange is your signal B, which is in the top, and magenta, the purple is your signal A, which is this one. Now, what about the output signal? Click here. Now look at the output signal, which is yellow. Okay, so let's now see how the Boolean expression of the NAND gate is verified. Your input B is logic 0, input A is logic 1, and the output is logic 1, which is NAND gate output, which is very fine. Here, the output of a NAND gate is logic 0. Why? Because both inputs A and B are at logic 1. Okay. Now again, you have logic high at the output because at this time, your input here is logic 1, but here is logic 0. And here it is logic 0 and here it is logic 1. Similarly, again, your output goes logic 0 because input B is 1 and input A is 1. So you see that we can verify all possible combinations of the NAND gate for this truth table. What about we just go back to KiCAD, come here, and here we have a pulse period of 2 micron. Here we have a pulse period of 1 micron. How about here? We just say the width is keeping same. Let's say 0.5. Can we see that? 0.5, and click OK, and then click the simulator button. Come back here, run the simulation and see how the signal can vary. Now look at this. Accordingly, your output is switching because you're varying the width. So this is how you can see in this module. We have learned how to separate the signals in the plot window. Earlier, in our earlier module, we got the signal, but they were all intermixed. So that was difficult for us to interpret the results. Now you can just play around with all possible combinations. For example, here you can say, I have a period of, instead of changing this, I want to change signal A. So instead of, let's say, 1 micron, I keep it 3 micron. And let us see how the simulation results will vary. I will click the simulation and see now how things will change. Now look at this. Here the logic is always high. That is the output. Why? Because for this time period, your inputs, one of the input is logic 0. And that is what it is showing up. Here the logic output goes 0 because both inputs are at logic 1. That is how the NAND gate works. So hope you found this model useful. Especially we learned here how to separate the signals in the plot window. If you want to understand this schematic, how we did that and how we added the spice model, everything we have explained in our previous module. So refer to that. Still then, wish you happy learning. Stay tuned, share it with others for wider reach.